Alright, so here are some problems from the OpenStax textbook. And oh, no, I clicked on something else. And I'm going to go down here to the first one, magnetic force, and there's a couple of things that I need to look up before I do this one. One of them is the right-hand rule itself, which is actually this one here that I accidentally clicked on for a moment ago. So here we go, and they do it, I think, I thought they did it somewhere here again, or maybe later or something. Okay, any case, here it is. So you have the velocity of a positive current or charge with the thumb, the magnetic field with the pointer finger, and of course the magnetic field is pointing north to south, and then the force that acts on that charge due to the magnetic field. So that's the Lorentz force. Now here they do the palm, and the palm points upward. That's what you find in American physics books, in German physics books, and I understand, there's something about not using the middle finger, but I have to tell you, it's just so much easier for me to do this one. If I could do this one, sure, or I can simply do this, and we can still see it. So here is the velocity of the positive charge, here is the magnetic field north to south, and then here's the force in which it will be deflected. So there it is. By the way, if it was a negative charge, you would have to use the same right-hand rule. I would say use the same right-hand rule, just make the force then in the other direction, when you have a negative charge flowing. Okay, so that's the first thing to review. The second thing to review, let me go back here, is that we're now in 3 dimensions, and which makes it hard to figure out, to draw it and to point at things. So here what they do is, for example, with the magnetic field, that this magnetic field is coming at you, so north to south, and this magnetic field is going away from you, so north to south. And so I pulled this one up, I compared to arrows, and if you look from the front, oops, no, it's a little too big. If you look from the front of an arrow, let's see which pictures I like the best. Almost this one here. And yes, there are others, and there's Jennifer Lawrence there. So when you look from the front, for any one of these, you see the point. So the arrow is coming at you. When you look from the back of the arrow, well, you're going to see this kind of cross here, or in this case, it's a triangle thing. So you're looking from the back to that. You can also think of the feathers in the back, which look kind of like two-dimensional here. I think in this picture down here, it's a little bit easier to see that, yeah, when you look from the back, you actually see kind of like a cross. So that's what we're looking at here for the magnetic field. It's going away from you, and here the magnetic field is coming at you. And I sure hope that my cursor is showing here. All right, so, and here, of course, comes the thing with, there's this webcam on here, so I hope this is going to work as well. So here it says, what is the direction of the magnetic force on a positive charge that moves as shown in each of the 6 cases? Alright, so this is the gazillionth plus 1 time take on these, and I better hurry up before my camera shuts down on me, because that's one of the reasons why I have to keep repeating this. So here I am, you're looking at the paper where you have these 3-dimensional Lorentz Force images, and then you're looking at my hand from the same perspective. So the right-hand rule will work nicely. You don't have to look at it, you don't have to turn your perspective. In any case, first one, these are all positively charged particles. So first one, velocity is down of the positive particle. The magnetic field is coming at us, and the force is to the left, and that's exactly what it says here. The next one, velocity of the positive particle is upward, magnetic field is to the right, and therefore the force is into the paper. And I think I'm going to go over here. Doesn't change anything but the right hand. So velocity up, magnetic field to the right, force into the paper. And I'm just going to call it as if this is printed out. This is paper, monitor or board, what have you. I just call it paper. Okay, velocity
velocity to the right of the positive particle, magnetic field at us. This is, we have to get to the other side again. Sheesh. Okay, velocity this way, magnetic field. Why is this doing it? See, that's why I have to keep doing take after take, because there's always something happening. So, velocity to the right, magnetic field into the paper, and therefore force upward, which is what it says here. Okay, velocity to the left, magnetic field to the right, which I can't do. I really seriously would have to break my finger to make the pointer finger point in the opposite direction. In any case, they have an angle between each other of 180 degrees, and the sine of 180 degrees is 0. So when they're parallel or in the opposite direction parallel, sine of 0 is sine of 180 degrees is 0, hence no Lorentz force, hence no force on that particle. The magnetic field has to make at least some kind of 0 angle to the velocity in order to get a force. Alright, velocity here actually into the paper, magnetic field upward, and force to the right. Every time I do that, as you notice, I do have to really do something here with my hand. Velocity coming out of the paper, magnetic field to the left, and force downward, which is exactly what it says. Alright, maybe this time I got it.
Alright, and I'm back, and I had this done already, this next problem. 9 minutes of recording, and then I noticed that, of course, my recording software figured that it's a good idea to turn the webcam off while I'm actually needing it. So, need to do the same thing again. As I said before, I'm not doing all the openstax text problems. I assigned a number of them. I'm not doing all of them. I'm just doing a few of them. So, it's just here and there you will find one. So here's one, Star Trek antimatter drive. Viewers of Star Trek hear of an antimatter drive on the Starship Enterprise. One possibility for such a futuristic energy source is to store antimatter charged particles in a vacuum chamber circulating in, by the way, I did make the same pronunciation error earlier, vacuum chamber, there we go, circulating in a magnetic field and then extract them as needed. Antimatter annihilates with normal matter, producing pure energy. What strength magnetic field is needed to hold antiprotons? What we find in our everyday world is protons. That's what we're made up of. We're made up of protons and neutrons in the nuclei of all atoms, and electrons that swirl around. These are the three parts that make up everything. And then we have a fourth particle, which is the photon, which is light. That's basically it, those four. And all the rest are just kind of like things on the side, bonuses or something. Anyway, the antiproton would be the bonus that if there were antiprotons existing in abundance, they would annihilate with the normal protons, and we would have a universe that would just have energy, which is gamma rays going around. By the way, fortunately, that is not the case. You actually would have to produce antiprotons in the lab, and that's possible. But fortunately not too many are around. In any case, they would actually annihilate themselves with regular protons producing gamma rays, and these gamma rays then they would take off, and then the action-reaction principle says that if a gamma ray goes this way, you get an equal and opposite force in the other way, and that would be the recoil here for this rocketeer going in the other direction, therefore. And so that part is actually true here. The rest, of course, is science fiction in here, the antimatter drive. But as I described, that part actually would work. So they're moving at this particular speed here in a circular path that's 2 meters in radius. Antiprotons have the same mass as protons, but opposite negative charge. So that's the difference. Antiprotons are the same thing as protons, but they have a different charge. They're negatively charged instead of positive. And yes, they annihilate with the protons. By the way, there is also anti-neutrons, and there's also anti-electrons. The anti-electrons actually exist more often in the lab, and so they have their own name. They're called positrons, and from that actually derives a medical diagnostic method, which is called PET, positron emission tomography. You'll find it in some hospitals around the world, actually. I'm going to turn my light back on. The sensor likes to go off frequently. All right, and then the second part is this field strength obtainable with today's technology, or is it futuristic possibility? Okay, I'm going to go over to this diagram right here. So here we have, notice there's a negative particle actually in this drawing here, and I hope you can see this one here. I'm going to hold it a little bit further up this time. So here I have the charge, the velocity of the charge is going upward. The magnetic field is into the paper, and therefore the force is to the left. However, it is a negative particle. Hence, the force is to the right. And you can see that in the drawing. Oh, and what I meant is I'm looking at the left of that circular path here where the velocity indeed is upward. And yes, the magnetic field everywhere is going into the page. And the force would be to the left if it was a positive particle. It's not. So hence the force in the opposite direction. So the force is to the right here, and we get a clockwise path. And by the way, if you turn this one here, as the particle is doing this here, then the particle is going to the right on top of that path. Magnetic field is still inward all the time. The force would be up if it was a positive particle, but it's a negative one, so hence the force is actually down. And again, you get that circular path there, this clockwise one. If it was a positive charge, by the way, it would be a counterclockwise circle. All right, the algebra behind it is written right here. I wish they would have written in here, this is Newton's second law. That's where it starts on the right-hand side, because it is a circular path. You have the centripetal force, so mass times velocity squared over radius. On the left-hand side, you have the Lorentz force, charge times velocity times magnetic field times the sine of the angle. The velocity and the magnetic field are perpendicular to each other, so sine of 90 degrees is 1, and you don't see it here anymore. In any case, there it is. And by the way, that's the only force that is acting on here, so the sum of the forces on the left is simply that. Do the algebra on that one. Notice there's velocity on the left, velocity squared on the right, so one of the velocities divides out, and then solve for radius, you get this expression. And now I can go back to the problem. Here again, there's Newton's second law, plugging that in, do the algebra. And then plugging in the numbers, you would have to look up the mass for the proton, which is the same as the mass for the antiproton. Velocity, that's given in the problem. The charge for the proton is the same as it is for the antiproton. It's the same as it is for the electron. It's the same as it is for the positron, always 1.60 times 10 to the negative 19 coulombs. The radius of the circular path is given in the problem, and here's the answer. And here's the calculator, and because I did this before, I noticed that the webcam never was on. I plugged this one in here, so 1.69, let's see, here it is, 0.261, right? Couple of things I want to point out. So this is correct answer, 0.261 Tesla. One of the things I want to point out is that when you type in numbers like this, parentheses around the numerator is not necessarily is not necessary actually if you have a multiplication there, but I still advise you to do that because it makes it look more consistent. I'm not going to retype the whole thing. I just, here's, by the way, 10 to the 7th and so on, close the parentheses. Then the parentheses around the denominator, that's the important part. So make sure that you put parentheses around the denominator, and then put them around the numerator as well anyway. So typical mistake of forgetting those parentheses. They're not necessarily written here. Notice over here they're only written around the numbers, but when you plug them into your calculator, you must have parentheses, especially around the denominator. Okay. Second question here. Is this field strength obtainable with today's technology, or is it futuristic possibility? Well, of course, there's a bunch of science fiction in here, but as far as the field strength is concerned, this is totally achievable. So the Earth's magnetic field is in the neighborhood of microteslas. The refrigerator magnet is in the neighborhood of millitesla, so that's about 1,000 times stronger. I looked these up. And then neodymium magnets, which I have here, they're in the neighborhood of 1 Tesla or so. So that's in the neighborhood of what we have here. So I'm going to attach this one here. I had to find some iron and metals in my office. And so here we go. You can see that this is hanging nicely. And by the way, I don't need all these here. I can just pull them off. And that takes quite a bit of force to separate them. There we go. And now I only have 4 left here. 4 of these little ones. And there we go. It still attaches nicely. Okay. Here is a, whoa, quite a bit of force. Misconception. Metals are good electrical conductors. That's actually true. The misconception is metals are magnets. No, they're not. Many metals, in fact, are not magnets. This one here is either chromium or aluminum or some kind of alloy. In any case, it's not magnetic. You have to have iron in there for it to be magnetic. Or nickel or cobalt, or in this case, neodymium. So some kind of alloy of that. Let's see this one here. Yeah, this one definitely looks metallic, and it's not. It's, again, some kind of alloy of chromium or something. So, yes, metals are good conductors, but they're not necessarily magnetic. Copper isn't magnetic either. This one here has some iron, quite a bit of iron on the top here. This is 500 grams. So, oh, I'm sorry, here it is. This one here, I use this as a pendulum. So this one here has iron here in the hook, especially on the side here. Actually not. This looks metallic, but some kind of other metal. Iron here, and it lifts it pretty good here. So I have, this is 500 grams. I'm lifting this one here so it's not dangling and getting away on me. So this is 500 grams, 1 pound that these magnets are holding up. So yes, they are strong, and they're only in the neighborhood of like 1 Tesla, and yes, that one would be obtainable. All right, second time around, I'm done with this problem.
All right, so this is the same problem actually as before. When I chose that, I didn't quite realize that. So the answers are actually the same. Earlier it was about the positive particle moving. Here it's the conventional current, which is the same thing. It's defined as the positive charge flow. So on the first one, current downward, magnetic field out of the paper, and the force to the left, and that's exactly what it says for a solution. On the next one, current, the conventional current going upward, the magnetic field to the right, and then the force pointing into the page. I would have to be on the other side, oh well. And that's what it says here. And then the rest is really the same. So current here to the I mean, as before, current to the left, I'm sorry, current to the right, magnetic field into the page, and therefore the force upward. This one here, no force. That was about me trying to break my fingers, so I can, my pointer is pointing opposite direction as the thumb, but in any case we get an 180-degree angle between the two, and the sine of 180 is 0. The current going into the paper, the magnetic force, I'm sorry, the magnetic field upward, and the force to the right. And here the current, and therefore the force to the right. Yeah, I said that. Here the current the current coming at us, the magnetic field going to the left, and the force is pointing downward, and that's how the current is deflected. And that's how the positive charges were deflected earlier. In this case, earlier in that example where I said, okay, we have that positive particle going downward, and then if we had a negative particle going downward instead, then we would have to turn it around. Here we have the conventional current going downward. That of course means that the electrons are flowing upward. So watch this. The solution is left for the conventional current. If we're looking at the electrons though, which flow in the opposite direction, then we have the negative particle going up, the magnetic field pointing at us, the force pointing to the right, but we know it's a negative particle, so therefore the force must be to the left, which is exactly what it says here. Notice that's kind of the difference from the problem earlier. Here the electrons and negative particles really do flow in the opposite direction, and therefore they still get the outcome of that is still in the same direction. Alright, yeah, the rest is the same. Okay.
All right, so next problem is actually my second take. I actually did make a mistake on my first take, which I erased now. In any case, this is OpenStax textbook, chapter 22, magnetism, number 88, the Hall effect. So it starts out with saying unreasonable results. So frustrated by the small Hall voltage and so on obtained on blood flow measurements, and then there's some numbers given. What's the magnetic field strength is needed, what magnetic field strength is needed, and then a couple of follow-up questions. Okay, the thing to keep in mind here that this is about blood flow and that there's a vessel of 1.50 centimeters diameter, and I think you can see me on the screen here is about this big, 1.50 centimeters. Okay, anyway, I'm going to go over here to the OpenStax textbook actually. So here is the Hall effect, and let's only look at the first drawing here because the electrons are the charge carrier, so they apparently, as the conventional current is moving to the right and the electrons are moving to the left, therefore they're of course the ones who carry the charge. That's, by the way, where I made the mistake in my first take that I deleted now, and in any case, yeah, I didn't pay attention that there were actually electrons in this drawing here. Okay, in any case, on the left-hand side, you see that epsilon, which is the electromotoric force or voltage, it says so here in the text as well. There we go. Ignore that actually for a moment. Also ignore that you have minuses and pluses on the bottom and the top. But do pay attention to that we have a magnetic field coming out of the paper, out of the screen, and that the electron is moving to the left. So here's the right-hand rule. Unfortunately, you're going to see it kind of like in reverse, because again you have to look at the screen and then you have to look from my point of view at my hand. So here we have the electron which is moving to the left, that's my thumb here. Then we have the magnetic field coming out of the screen, and then we have the force, the Lorentz force, pointing upward. There it is. Boy, oh boy, oh boy, that's tough. So here the force is upward, but it's a negative charge. Hence, the force is actually supposed to go down, which we see in the little drawing right there. And we see it also over on the hand here where they put that hand there without breaking their hand. I'm almost breaking my hand every time I do that here. So in any case, the electron is moving downward due to that magnetic field. And therefore, the electrons are accumulating on the bottom here, which means holes are left behind. So we have positive charges on the top here. And we get now that EMF or voltage across here, which is the Hall voltage, which is the Hall effect. So we can actually measure that, and it's a matter of measuring the magnetic field. So that's how magnetic probes are actually are used, and a number of other things. I'm going to point those out in a moment. So here in a moment they actually will talk about you can do that with blood flow. Let's see, somewhere here it says something about charges in blood. There we go. I think here. Another application of the Hall effect is to measure fluid flow in any fluid that has free charges. Most do, so apparently blood itself also has some free charges, ions that flow with it, so you can actually measure the Hall effect with that, and therefore it is applicable. Another one is this one here, if I get it right. Yep. So this one is a current clamp. And if I can move this around, I guess I didn't make this small enough, current clamp. This is a no-contact ammeter. So instead of putting an ammeter in the circuit, you actually clamp this around. So this, you see the release here, and then this opens. You can put it around the wire, and the wire develops a magnetic field. And when you measure that magnetic field with this Hall probe, that's actually what this clamp meter is. Here it talks about the Hall effect being used for these. Then you can actually measure the current in that wire without actually disrupting the circuit. So very convenient. Okay, let me go back here. So here we go. Where was I? Let's see. So here, first drawing. I only pay attention to that because the first drawing here, because that's the electrons that are flowing here. So they feel a force down here, and then we get a voltage here, which can be measured, and therefore you can figure out the magnetic field or something else. The Lorentz force applies at some point. You have a buildup of negative charges on one side, positive charges on the other side, so you have an electric field as well. And what we see here is actually Newton's second law: sum of the force equals mass times acceleration, with the acceleration actually being zero. At some point you have enough charge build up here that the electric field force, so charge times electric field, is actually equal to the Lorentz force, and you come up with 0, which means they're no longer accumulating at the bottom here, but they actually now go straight through. So there should be a bunch of negatives in here. In fact, this apparently comes from the left-hand side. So this here started out with negative, which makes sense because the charge of the electron is negative. And this one here is a negative charge again, that, by the way, divides out. And then you have the electric field here, which points from up to down, so that's actually also negative in the drawing. By the way, up and down here does not mean that gravity is involved. This could be flat on a table. So, and then you do a little bit of algebra here, and then you come up with this kind of expression here. This here would be the width of, they put an L here for width, not length, but L for width here for this Hall effect probe here. And then here they have something for the blood vessel. So apparently here you have the magnetic field, obviously. And then here, perpendicular to that, that's where you would put the whole probe. That's where you measure the voltage. One little thing to point out here is that the EMF or voltage is that little epsilon here, and they do it correctly right here. They keep that epsilon for the voltage and the capital E actually for the electric field. And now when I go back to the actual problem, let's see, there it is. They unfortunately made a mistake in just a moment. So in any case, as I said, in order to solve the problem, start with Newton's second law. Then here is the force with the electric field. Both of these are from the drawing that we saw there are negative. And the others here, the charge is negative, and I guess the velocity is negative because it was going to the left. So magnetic field is also negative. So everything is negative actually in here. So the first one here is a positive number, negative times negative, and the next one is actually a negative, coming out to 0 at some point. Then the electric field is defined as voltage over distance. That would be here the width. And then this one here would mean then you get magnetic field is voltage divided by the width and the velocity. And then you solve it apparently here for the voltage, and this is where they made the mistake in their solution manual. Notice that they shouldn't say capital E here anymore, which stands for electric field. Instead, it should actually say either capital V for voltage or the epsilon or the EMF. Okay, in any case, you plug in these numbers here that are given in the problem, and when you do that, you come up with 111 Tesla. And then the problem is that we cannot achieve a magnetic field this great in the laboratory. These neodymium magnets that I showed, they have magnetic fields about 1 Tesla, and then I looked it up. The largest magnetic field that can be sustained in a laboratory, apparently in a lab in Tallahassee, Florida, was 45 Tesla. So that's still quite a bit low. So you cannot actually maintain it for a typical hospital, medical physicist who is frustrated. And yes, the assumed 0.5 volts output is much too great, probably 1 to 2 orders of magnitude too high, so that explains the unreasonable result. The other interesting thing is actually the 1.5 centimeter diameter vessel. I mean, this is this much. Is there any blood vessel that is that big? So I would think if we reduce that one, I think we would come up with a better estimate as well. All right, that's this problem. All right, next problem. I think after 2 days, I think I'm finally able to grapple this easy problem. And boy, did it ever give me the fits. I explain it in a little while when I actually get back to it. I want to review a couple other things before that. One of them is right-hand rule number 2 in the OpenStax textbook, and then even from there I'm going to go back to Wikipedia. So let's see where I am if I click on here. Okay, that's actually, I'm going to get to that relatively soon, but this is where I want to go. So right-hand rule number 2. By the way, here's right-hand rule number 1. There it is, right? So if you can see this here on the screen, so right-hand rule number 1, the velocity of the positive particle going this way and the magnetic field going this way on my pointer finger So thumb, pointer finger, and then the middle finger here upward, that would be the force on a positive particle. If it's a negative particle, force would look point in the opposite direction. That's the Lorentz force. That's right-hand rule number 1. Right-hand rule number 2 is, click on here, there we go, is that you have a current going through here, and this is the conventional current going through here, and then you wrap your hand around it, and you get the magnetic field, and a magnetic field, of course, pointing from north to south around the wire here. Okay, then I'm going to go to Wikipedia. Actually, before I do that, I think I'm going to, oh yeah, here we go. This is actually my website, or my Blackboard. So here's right-hand rule number 1, current, magnetic field, and force. Here's right-hand rule number 2, and this one here is current is the thumb, and the magnetic field curls around. And here is yet another one, which is right-hand rule 2b, which is basically the same as the other one, but just expressed in a different way. If you curl your fingers instead around where you have the solenoid, there's this curled wire there, and now that is actually the current, and the magnetic field is the thumb. And that's actually, this one here on the right is the same as this one here, just expressed differently, and switched thumb with fingers, one of them the current, the other one the magnetic field, and then the other way around. But it is actually the same. That one I actually did get from Wikipedia. I finally found it there. So here is the typical one that you will find, right-hand rule 2, and this is the alternative way of showing it. And there was still one that I saw somewhere. I have to find it. I think I get it later. All right. And indeed, I just found it. It's on the same OpenStax page here. So right-hand rule number 2, there it is. So the thumb is the current, which is in this case the solenoid going around, and then the magnetic field are still the fingers that would curl around the wire, but because we have the solenoid, now the magnetic field is actually kind of straight around here. And if you can see this one here, thumb, the curled current, magnetic field, the fingers pointing inward. Well, if I switch them, watch this, there is my current going in the same direction as it was before, and my magnetic field pointing in the same direction, except I swapped the thumb with the finger. So this particular image here in the OpenStax textbook, which is chapter 22.9, actually shows what I called the rules RHR2, right-hand rule 2, and right-hand rule 2b. All right. I'm going to go back. Let's see where I was. Here. So I want to do the very straightforward problem 5, and then it turns out it's not so straightforward. So I'm going to actually do these two first. Number 1.
All right, so this is about the induced current, Faraday's law, magnetic flux, Lenz's law, and also the gazillionth take that I have on this one, and trying to figure this out, and then overlooking one little thing. I will show you that in a little while. So here's the original problem that I actually have on the homework, but let me go back a couple. You will find these in the OpenStax textbook. So the question here is that you have a current going through here which produces a magnetic field, and here of course we have right-hand rule number 2, and then I amended that to right-hand rule 2b. So right-hand rule 2 is that you have the conventional current here, and the magnetic field wraps around it, like this one here. You would have the magnetic field wrapping around it, north to south, going around it. Here you already have the current in a coil, in a circle, and by the way, I kind of mind this one. I know they cut it off so that they don't need more wire here, but technically this looks like a disrupted circuit, but it's not supposed to be, and they say, hey, this really is a circuit, so this continues on. So we actually have this as a circuit. So right-hand rule 2b. when you look carefully at a solenoid, and I think they actually have that in the OpenStax textbook where they show you that, then you interpret this one here as being the circular current, like this, and then this here, the thumb, now becomes the magnetic field. And if you compare that to current, magnetic field wrapping around, and current wrapping around versus magnetic field pointing that way, again north to south, you will see that actually is correct as you take this Y here and make a loop out of it. Okay, so hence right-hand rule 2 and right-hand rule 2b is what I call it. So this one here, magnetic field, current curled, magnetic field pointing this way, which means this one wraps around now like this, so the magnetic field is going this way. And no matter if it's constant or if it's actually changing, so if we have actually a changing magnetic flux here, it's bypassing that coil, and you can see that from the equation. The angle between the two coils is 90 degrees. The magnetic flux takes on the cosine of the angle, so cosine of 90 degrees is 0, and yeah, no matter what is happening here, current increasing and therefore magnetic field increasing or decreasing or constant, doesn't matter, it's all bypassing that coil and you don't get anything here. So it's simply just 0, nothing will happen here. Okay, the other wire here, current, magnetic field again actually bypasses this coil here, so it goes like this, and no matter if it's increasing or decreasing or what have you, it doesn't change anything, you don't get anything in here. Again, you have that cosine of 90 degrees, which comes out to 0. Okay, next diagram. Oh, one thing to point out. From our point of view, and it's made clear in the problem, this one is a top view, which means the coil is lying flat on the paper, or the monitor, let's call it just the paper. And here we're looking at it from an angle, in fact, like it's 90 degrees, it's going into the paper. That's how these coils look like, right? Remember that for later. Next drawing, it clearly looks like they're lying flat on the paper. All right, current curling around here, right-hand rule 2b, magnetic field pointing at us. Now it needs to wrap around to get to the other coil, which means the magnetic field is actually pointing this way. And now the magnetic flux is increasing, so we have an increasing magnetic flux going in. Lenz's law for this one here, and review the rules for analyzing Lenz's law. The magnetic field for this coil here must be pointing this way at it, opposing that, and therefore this one, right-hand rule 2b, that's the electric current that we have in the second coil here. And if this one is increasing, the magnetic field, the magnetic flux, then we have a current that is going counterclockwise, and that's the answer to the question. If this one is a decreasing magnetic field, which means the current is actually decreasing, so decreasing magnetic flux, then it's curls around here, and now this one is actually decreasing, and that one is actually opposing it, which means that the magnetic field is pointing into the paper, and we actually get a clockwise current going around. Notice that as I do this one here, that's quite difficult to do, right? In 3 dimensions here with my hand, even worse than the right-hand rule. Right-hand rule I think is straightforward with Lorentz Force. This one's really a lot more difficult. All right, this one here, the electric current pointing this way. I think I'm going to go to the other side. So current going this way, which means magnetic field is wrapping around, right-hand rule 2. Which means it's grabbing in there right now, and if I have a current that's increasing, I also have a magnetic flux that is increasing, so it's pointing into it and increasing. And again, Lenz's law, that magnetic field that opposes it, actually I think I can keep sitting on the side here, that magnetic field that is opposing it must be pointing at it, so out of the paper, and I get a counterclockwise current in here. This would be right-hand rule 2b applying to it. And if I have a decreasing one, well, then my magnetic field was still pointing inward. Here's actually decreasing. This one is opposing it, so it's pointing inward, and I have a clockwise current. Again, when you review rules for Lenz's law and how to analyze it. If it's not changing at all, well, then I have no change in magnetic flux, and Faraday's law tells me that I don't get a secondary current in the other coil, and both of them would be, there would be no effect. I don't get any current there. Okay, again, review this one here, all right, that these are flat. There's another flat one, and this one here is from an angle, right? That's the way it looks like. And now we go to this drawing, and looking at these other diagrams earlier, they all look like they're in 3 dimensions. They're going into the paper, except that's not what the problem says. It says they're actually lying in the plane of the circuit. Well, if you do that, why don't you just make them circular? So it looks like they're looking at it from the top. I think they made the wrong diagrams here. They should have made the circles, and it would just look better. Okay, this is actually basically the same thing that we just looked at with the straight wire. So the conventional current is going upward. I think I have to go to the other side. Conventional current is going upward. This going into the loop, which is supposed to lie flat here. Magnetic flux is increasing. Magnetic field is pointing outward. And therefore I get a counterclockwise current, which is actually exactly what it says here. On the other side here, oh, this was actually part 2 over there. Yeah, then they mixed also up 1, 2, 3, and here they call them Roman 1, 2, 3. Oh well. Okay, so actually this one's still counterclockwise. Conventional current on the other side here. So current is going downward. Do I want to be on the left or the right? So current going downwards, magnetic field pointing into the loop, and then increasing magnetic flux because the switch is just turned on, so the current increases and the magnetic field increases and the magnetic flux. Alright, so my camera actually stopped filming there after 8 minutes or so. So I think I just had finished this one, so I'm going to do this one here and then I'll just edit them together straight away. So in any case, the current here flows this way, so I have a current going down, magnetic field is pointing in, and then of course it's an increasing current, hence increasing magnetic field, hence increasing magnetic flux going into the loop. That loop, right-hand rule 2b now, means that its magnetic field must be opposite of that, pointing at the original magnetic flux, and so I get a counterclockwise current in here, which is exactly what it says. Okay, part 3, this gets interesting. Right-hand rule 2b, because this is a coil, and this one really looks like we are in 3 dimensions, right? Here's the coil. So it has that current here, which means I have a magnetic field to the left, and then the current is increasing because the switch was just turned on. So my magnetic field here is increasing and the magnetic flux is increasing, and then of course it wraps itself around out of that coil into the other coil, but the other coil is flat. That's what it says in the problem. So the magnetic flux, the magnetic field, is actually bypassing that. Okay? And so as it's bypassing that, we again have the cosine of 90 degrees, and that is 0. And hence we don't get anything, which means their answer over here is wrong. There's actually no current, and I think I fixed that in the homework sheet. So if they really want to do it right, they should say, okay, we make nice circles here, and here we actually make this loop that is at an angle pointing into the paper. I think I already sent something to openstax to fix this particular problem. Okay, the second part here, by the way, is they're completely right, by the way. The switch is closed, so we have a constant current going through here. That means we have a constant magnetic field. I don't know why this turned off here. I do know why it's turned off, because I didn't touch anything for a while. So we have the constant electric current going through here, constant magnetic field, which means the magnetic flux is not changing, and Faraday's law says that we therefore do not induce a current. You need to have a changing magnetic field, changing magnetic flux, in order to actually get an induced current. So a constant current here, in this case DC current while the switch is closed, it's just not going to work. No, nothing is induced. Okay. Then the switch is being open, at which point we still have the same thing as before, the magnetic field pointing this way, but this time it's being reduced. And therefore, again, the magnetic field is opposing that, but now it's pointing inward. And for this loop here, we get a clockwise rotation. And for this loop here, we get a clockwise rotation. And again, if we assume that this one is actually flat, which it doesn't look that way, we actually get nothing there. Actually, let's assume that this one is actually tilted into the paper here. So here I have this current here, right-hand rule 2b. This is the current here. This is the magnetic field, which wraps itself around into the coil, but now it's decreasing. So this one is decreasing, which means the magnetic field in the coil here is actually pointing this way, and I actually get, yeah, a clockwise rotation out of that. I think I did that right. Yeah, I think I did that right. So, but again, from their point of view, it's, there's actually no current over there because they assume that this is flat. All right, I think I got it.
Overall, unfortunately, I chose that, but hey, you got a, boy, 14-minute mini lecture out of this one here for this particular one, yeah. All right, I think I'm done with this one. By the way, if this number 3 here, okay, I'm not done. If number 3 actually was tilted the way, it doesn't say so. It says it's in the plane of the circuit, but it looks like it's tilted. So if it was tilted, yes, then we would have a magnetic flux into it, and then we would actually get a clockwise or a counterclockwise direction of the current in here. Of course, and then the other thing is actually, these look like they're disconnected, right? It's like they're broken, which means we have an open circuit. Nothing will happen in an open circuit, but what they mean is they can just continue on, okay? As opposed to this video here, not this guy, but this guy, this one here really is a copper ring that is being totally closed, which means we have a closed circuit here with the induced current, and you can see that nicely in this video. And here, this is a gap. This is a true gap in there. So this is an open circuit. Nothing will happen there. No induced current. Nothing will happen. Okay. Anyway, I think I'm done now. Oh, great. Still not quite done, so I should go back here. So as I said here, for number 1 and 2, counterclockwise, that's what I said earlier or recently. And then this one here is actually none, no current. This one here, part B as well, where you simply have the switches closed for a long time, like it says in the problem. And yeah, constant current means that you have a constant magnetic field, so you have no changing magnetic field, hence no induced current in the coil. And then they did something else strange here, unfortunately. They call these 1, 2, 3. When they call it 1, 2, 3 this way instead of going across? Anyway, and then over here they actually named them in solution manual Roman 1, 2, and 3. Well, this should be the case here, so I'm going to fix this one here. And then the opposite way is when you open the switch. Well, now the current decreases, which means the magnetic field decreases, and of course you have them in the opposite direction. And again, for the number 3, which is the one in the middle that's parallel, more or less parallel to the coil, the solenoid, actually you have no current there because this, yeah, parallel to the magnetic field. Okay, now I'm done, baby, hopefully. All right, next problem. Car generator turns at 400 RPM when the engine is idling, so that's relatively slow. 3 in a turn, 5 centimeters by 8 centimeters rectangular coil. That's not very, I mean, that is small, you know, it's 2 inches by 3 inches, typical for a generator, I guess. Rotates an adjustable magnetic field so that it can produce sufficient voltage even at low RPMs. Was the field strength needed to produce 24-volt peak EMF, electromotoric force. Discuss how this required field strength compares to those available in permanent electromagnets. Okay, so let's see. I'm going to go over here. So this is the OpenStax textbook. This is section 23.5. So here you have a generator, and here you have the loop that would be the 5 by 8 centimeters that they describe here. Here, of course, the magnets, and then as it rotates through here, you get the magnetic flux that is changing over time, which then induces a current in the loop right here. And the only thing that you don't have is, well, you're not rotating it with your hand, but it says right here, coil rotated by mechanical means, which in this case would be the engine actually rotating it. All right, then you have these formulas here. Here's the magnetic flux, and then because the angular velocity is given, problem to 400 RPMs, you're going to go through the motions of the algebra, and you end up with this equation, I believe. Let's check that in a moment. I think that's right. You end up with this one here, and then you solve this one for the magnetic field. So let's go back. Yes, I was right about that. There we go. First of all, the RPMs are given as 400, so you have to get it into standard units, so per second, rads per second as it says, respectively hertz. And so here's the calculator and whatever I calculated there before. So 400 divided by 60, so you have rounds per second instead of per minute, and then multiply by 2 pi because you need to get it into radians. And there, of course, is the 41.89 rads per second that they say here. And then you take the other equation. And again, this here should be, in my opinion, should be an EMF or epsilon or V for voltage. The E, capital E, should be taken up for electric field. Oh well. Solve for magnetic field. Oh, I just noticed they made a mistake here. There should be equal right there. It shouldn't be times, it should be equal. Okay, the rest is given. So there's the 24 volts divided by the 300 turns of the coil. So it's not a single one like you saw in the picture, but it's lots and lots. 300, and then this one here, of course, is the size of that loop. The 5 by 8 centimeters in meters, of course, and also divide by the angular velocity. So what I just had, so plugging that one in, these numbers here, I think I'm going to put that on this side here. So again, there should be B equals that. So let's see. The 24.0, that's the numerator, divide by, open the denominator, 300 times the 0.05 times 0.08. Of course, I could type those zeros, but the calculator actually doesn't care. And then I divide by, or I multiply by the answer in the denominator that I just had. And then I closed my parentheses for the denominator, hit enter, and there, of course, is the 0.477 Tesla that it lists as the result. And let's see a little bit here. Yeah, this field strength is small enough that it can be obtained easily using a permanent magnet. Actually, it seems like a strong permanent magnet. Refrigerator magnets are in the neighborhood of a few millitesla. This one here is getting actually close to these neodymium magnets, the really strong ones. However, if you actually do look at an electromagnet, they are pretty powerful. So they are in the neighborhood of 1 Tesla or so. And you can also look at this one here. Orders of magnitude, which I pulled up right here, and actually that's what I just said a moment ago. Here is the millitesla refrigerator magnet. Let's see, strength of neodymium, rare earth magnet in the neighborhood of 1 Tesla or so. And then here, or for example, here inside the core of a power transformer, also about 1 Tesla, and that's similar to the magnetic field that you would get in a generator. All right, that was that problem. All right, and the last problem that I want to do. So transformer, plug-in transformer for a laptop computer puts out 7.5 volts and can supply a maximum current of 2 amps. What is the maximum input current if the input voltage is 240 volts? Assume 100% efficiency, and then if the actual efficiency is less than 100%, would the input current need to be greater or smaller? Explain. So use the transformer equation from 23.7, and that is straightforward. So here it is. These are, let's see, I'm going to get these on the screen here a little better. So that's from the OpenStax textbook. So here are your typical transformers, and this is how they look inside. So you have a primary voltage here, then you have the coils around here, and notice the number of turns, and then you have the secondary one, and notice that there's a different number of turns here, and then you have the iron core going around here, which funnels the magnetic field from one coil into the other. And then it turns out that you have these simple ratios of the voltages are, the ratio of the voltages is the same as the ratio of the number of turns, and the ratio of the voltages is the same as the ratio of the electric currents. Just notice secondary versus primary, primary versus secondary, and then the same thing, of course, currents versus number of turns. So really simple transformer equation. Okay, going back here, this is what it's asking for. What is the maximum input current? So you use their effect. Here are the three ratios in one equation. you need this one here, so you don't need the number of turns, and then you plug in numbers. 2 amps is the secondary current that you want to get out. 7.5 volts is what you want to get, and then 240 volts is actually what you put into it. Yeah, your laptop computer does actually not like 240 volts that you get from the outlet. Or in this case, must be in a foreign country, right? Because in the United States we mostly have 120 volts. So you need to step it down that voltage to get less out of it, and then you get this amount of current. So the primary current comes out to this when you multiply 2 times 7.5 divided by 240. So the original one is only 0.063 amps, and then, and I mean I can show this on a calculator, but you can also do it yourself. And then if the efficiency is less than 100%, yes, then you would need the input current to be greater in order to get the same amount of power out of it. And that could happen because within a transformer you have energy losses due to heating up of the transformer. And touch the transformer when you have your laptop plugged in, and you will notice it's getting warm over time. All right, and I think that was the last problem I wanted to do for this unit for some of the homework problems.